All right, this is Physics 1B for the evening section for October 13th. Tonight we're going to be talking about the topics that are written right here. Thermal properties of matter in terms of equations of state, the ideal gas equation, which a lot of you have probably seen before. We're going to talk about PV diagrams, and then we're probably not going to talk about number 4. We're going to jump into kinetic molecular model of an ideal gas. You can read about number 4 in the textbook. It's a pretty short section, and there's not really any math or problems we can do with it. Okay, so equation of state. What is an equation of state? An equation of state is an equation that describes the evolution of a system It's the equation that describes the evolution of a system's properties. And it does so. The properties that it's going to use are going to be things like pressure, volume, temperature, things like this. Maybe some other things as well. But it's an equation that's going to describe the evolution of a system's properties over time. So if you know what they are at one point in time or at one particular value of these quantities, you can figure out what it's going to be later. An equation of state is somewhat similar to when you are writing down an equation of motion for a particle. So for example, if you're looking at a projectile that's flying through the air, then you can write down the position as a function of time for that projectile. You can know where it's going to be and what its speed is going to be if you know what it is at one point in time. An equation of state is pretty similar to that. This is an example of an equation of state for a solid. Right here. Now, part of this equation you've seen before. The part where it says V equal to V naught multiplied by 1 plus beta times T minus T naught, that portion is the kind of volume expansion equation that we've seen before. Add to that is another term right here that depends on pressure, okay? There's a negative sign here. It says because an increase in pressure causes a decrease in volume. So what does this equation actually do? It tells you what the volume of your solid is going to be if you tell me what its volume is at some particular temperature, and you also know at that same temperature what the value of the pressure is, and then you tell me, okay, now here's a new pressure, and here's a new temperature, what's the new volume going to be? That's all it is. That's an equation of state. And obviously you know that this quantity beta depends on what type of the material it is. The quantity K will also depend on what type of material it is. Okay? Now we're not going to use that equation very much, but it's just to show you that that's what an equation of state basically is. Okay? Something we've kind of seen before already. The one that we want to talk about tonight is called the ideal gas law. And it is described right here. There it is. That's what it looks like at the bottom. Now, in the case of gases, we're going to be talking about what are called ideal gases. And an ideal gas is one in which we make the assumption that the molecules are very small relative to the total volume. We also make the assumption that they don't really interact with each other very much, so they don't feel forces. And we also assume that when they bounce off walls, they don't lose any energy. That the collisions that they feel with walls, and if they happen to collide with other molecules, those collisions are perfectly elastic. That's what we call an ideal gas. It turns out that it is a pretty good description for a lot of gases. The ideal gas law is, okay? So the ideal gas law is an equation of state that depends on pressure, volume, temperature. But then one new thing here, which is little n. Little m is the number of moles of a substance. The number of moles of a substance is directly a measurement of how much stuff you have. It's a measurement of how much stuff you have, okay? 1 mole, what is 1 mole? You all tell me, what is 1 mole? What is 1 mole? It's that number of what? It's 6.022 times 10 to the 23 atoms. Or molecules. Yeah, atoms or molecules, right? It can be atoms, it can be molecules. And that number is Avogadro's number. That's exactly right. Okay? So 1 mole is 6.02 times 10 to the 23 atoms. All right? So that means that if I tell you I have 5 moles, then that's 5 times this, which would be about 30. 30 times 10 to the 23 atoms. 5 moles is the same thing as saying 30 times 10 to the 23 atoms, but it's a lot easier to say 5 moles than it is to say 30 times 10 to the 23 atoms, because we don't really understand what 10 to the 23 is, right? Now, we understand small numbers. Like, if I tell you I have 15 oranges, you can envision in your mind what 15 oranges look like, right? But if I tell you that I have 1,000,000 oranges, you don't really have a good understanding of what 1,000,000 oranges is, right? If I asked you how many trucks do I need to put a million oranges in it, I don't know what the answer is. 1, 2, 20? I'm not really sure. You know what I mean? 1,000,000 oranges is a lot of oranges. It's probably going to take a lot of trucks, right? So a mole is a way of taking a number that we don't really understand, like 10 to the 23 atoms, and turning it into a number we can understand. Because we can count 1, 2, 3, 3.5. We understand what these things mean, right? So that's what a mole is for. We use n for moles, and there's a relationship where if we take little n, okay, and we multiply by what's called the molar mass, capital M, this is going to give us the mass of the substance, okay? So capital M is molar mass. What do you all call it? Is that what you call it in chemistry? Maybe you use mm or something like that? I feel like I've seen people use mm when I see them working on chemistry problems. Is that what you use? But you still call it molar mass, right? This comes from the periodic table. Let me show you where it shows up. Someone linked a periodic table in here the other day that was really good. We'll click on that one. See if I can find it. Where did it go? Well, I can't find it. So we'll just pull one up on the internet. So on the periodic table, you can find this thing called molar mass. Does anyone want to tell me where you find it? Where do you find that number on the periodic table? You did use M, capital M? Okay. For molar mass. So where do you some people should be familiar with it though. Where do you find it? So I pull up this periodic table of elements right here. Where do I find the molar masses? Let's say I go to copper. Here's copper. There's a 29, there's an 11 above it, there's a Cu, there's something that says copper, and then there's this number at the bottom, 63.546. It's at the bottom. Yeah, you all know the answer. You just need to see it. It's right here. It's this little thing that shows up here at the bottom. Every element has it. Hydrogen has a molar mass of 1. 1. What are the units on that? What are the units on this? Let's do it for copper. Copper is 63.546. So the molar mass of copper is 63.546 AMU? No, that's not right. That's not what the units are. What are the units on this? Come on, let me just erase. What the hell? What's wrong with this thing tonight? 46. Grams per mole. Thank you, Sergio. That is right. This is grams per mole. Okay? So, it's a way to go from moles to grams, right? So, for example, suppose that I have... so, if I give you 30 kilograms of copper, how many moles does it have? Oops. We can also ask how many atoms. All right. So if I have 30 kilograms and I want to convert it into moles, that's what this is used for. Okay? So what you can do is you can say 30 kg multiplied by this coefficient here, 63.546, grams per mole. Oh, yeah, so we'll write it like this. I'll write grams down here, and then I'll write 1 mole up here. And then I just need to convert from grams to kilograms. So there are 1,000 grams in a kilogram. Just do a little conversion factor thing here. And this, you can't see it, is going to be equal to... So it's 30 over 63.546. Times 1,000. 472. So this is the number of moles, would be 472 mole. That's how many moles of atoms we have, right? Does that make sense? This is a very powerful idea right here. The fact that I can convert from grams, which is mass, to moles, which is amount of substance, is extremely powerful. Very powerful. And you're going to need to do it in some problems to find this quantity here in. All right. What about the number of atoms? Well, we know that 1 mole corresponds to this many atoms, so we can do another conversion factor here and say 472 mole. And now we multiply by this conversion factor. We turn that into a conversion factor. And we put mole in the bottom. You put atoms in the top. Right? And then that will give you the number of atoms, which I'll use capital N for, because this will come up later as well. And that would be, so it's 472 times 6.02. So we'll take this number that we just got, multiply by 6.022 times 10 to the 23. There we go. 2.8 times 10 to the 26 atoms. It's a lot of atoms, I guess. I don't really know how many a lot of atoms is, honestly, but it's a big number. Atoms are unimaginably small, though, right? Because 30 kilograms is something that you can imagine. 30 kilograms is like 60 pounds, right? 60 pounds is very, very understandable. Like, you can imagine going to the grocery store and buying a 60-pound bag of dog food, for example. You could pick that up and you could see what it would feel like, you know? This is how many atoms you would need to get 30 kilograms of copper. You need a ton of atoms, which means an individual atom is very, very, very tiny. Has almost no mass, basically. Okay, so that's a new topic for those of you that haven't taken chemistry. If you have taken chemistry, this is probably review. But again, just to review, what is N? N is the number of moles of a substance. It's the way that we count the amount of the substance that we have. And 1 mole represents 6 times 10 to the 23 atoms. And you can use molar mass, capital M, with this equation right here. It's basically what we did. We took mass and see, this is basically here, this is mass, right? And this was molar mass. We basically just did big M divided by, little m divided by big M, give us capital little n here. So, there we go. Anyone have any questions? I know it looks like it, but there's nothing getting cut off over here, by the way. It's just... Okay, so let's get on to the ideal gas law. What the ideal gas law is going to do is it's going to tell us if I know pressure, volume, and temperature, and I tell you what the value of this gas constant is here, so capital R is a gas constant. It has 2 different values. One of them is 0.08. Is it 02? It's 0.08206. The units for this one are liters times atmospheres divided by moles times Kelvin, okay? Unlike in problems that we've done in the past, you must put temperature in Kelvin to properly use this. The other value of R that you're going to see show up is 8.3145. This one is in joules divided by moles times Kelvin. If you've taken a chemistry class, you probably almost exclusively used the upper R value right here. And the value of R that you choose depends on the other units that you use in the problem. So since the equation is PV equal to nRT, then if you measure, you're always going to measure N in moles. You're always going to measure T in Kelvin, okay? So the question is, how are you measuring pressure and volume? If you measure pressure in atmospheres and you measure volume in liters, then you use the first R. Does that make sense? If you measure pressure in atmospheres and volume in liters, you're going to use this one. Okay. For the other equation, for this one here, if you measure your volume in meters cubed and you measure your pressure in pascals, then you use this one. Doesn't matter which one you use, but you just got to make sure you use the right one for the units that you're using in the problem. But yeah, this thing gives us the relationship between all those quantities. Now, how do we know it's true? This is an experimentally determined relationship, and we can go through and we can actually verify it by using, we can verify each one of these things here by using, where is it? This thing right here. So here what we have, just to show you, is there's a container, okay? We can fill it up with gas molecules by doing this. We got some gas molecules in there, right? They're going to kind of jiggle around, and they're going to diffuse out until they've evenly filled out the entire space after given some time. So that's our gas right there, okay? We can do things like we can heat it, and you can see that the temperature will go up as I heat it up here, right? You'll notice that also the pressure increases as the temperature increases. Probably not too surprising. You can also see that if we increase, well, tell me what you think is going to happen. If I increase the volume by moving this slider to the left, what do you think will happen to the pressure? Will it go down or will it go up? So if I give it a larger volume, basically, you think the pressure is going to go down? That seems reasonable. Let's see. So let's make it like a little bit bigger. Notice the pressure right now is 55.3 atmospheres. If I let go, yeah, I went way down to like 37. Okay, not too surprising. What happened to the temperature? Did the temperature change? It looks like no, right? Looks like the temperature didn't change. And that makes sense too, because if we don't add any energy to the system, how could the temperature change, right? After all, that's how you change temperature, we've learned, right? Q equal to mc delta T. That's still true, right? The only way to actually increase the temperature would be to add energy to the system, right? Okay. Now let's go through each of these terms here and let's see if it actually is true, okay? Right here, the first one says, the measurement of the behavior of various gases led to 3 conclusions. The volume V is proportional to the number of moles N. If we double N and we keep the pressure and the temperature constant, the volume doubles, okay? So what we need to check is that if we hold pressure and temperature to be constant and we double the number of moles, let's see if the volume doubles, okay? So how do we keep pressure? I think it's this button here. Maybe it's this one. We're going to try. I think that's what it is. Not 100% sure. Okay, ooh, let's go to exactly 400 here. Okay, so that is our system. I hope I did this right. I think this is the right one. We want to hold pressure and temperature constant. I'm a little bit worried this isn't going to do it, though. Let's see what happens. So we're going to bump this up to 800, and the goal is to see if the volume doubles. And the only really way to tell that in this case is by putting this little thing on here. So let's get it down to exactly 10. There we go. Oh yeah, it's, I think it's holding temperature constant. I think it's doing it properly here. Did the temperature change when I did that? Yeah, it did. Okay, well, that's not the button we want with this stuff. But then this can't move. Right? This won't move now. Oh, no, it will. It doesn't look like it will, but it will. Okay, so this is our initial... Okay, we'll go to 400 here. So according to what this thing says, the volume V is proportional to the number of moles. That means if we double in by keeping these things constant, the volume should double, right? All right, let's do it. So if I go from 400 up to 800, what should the width of this box be then? What should the width of the box be? If I go from 400 up to 800, what's the prediction? 20.8. Let's see if that happens. 44, 50, 500. Oh. Volume would be too large, huh? Well, we're going to go down to 300 now. All right, let's make it 5. Let's do that. Let's go from 300 to 600. Okay, so it's 5 now. You all said before that it was going to double, right? So it's going to go from 5 up to 10, right? Let's see if that's true. From 300. Well, okay, really? Because that? Okay. All right. We did that one, right? Yeah. Okay, let's try this again. Okay. Oh, no, we wanted to go... Here we go. This one's probably the worst one. The other two hopefully will work a little better. So we go from here. Oh, it's this one. That's the one we want, right? Okay. Now we double this. It should go from 5 to 10. So we go up to 600. 6. Boom. Now it's at 10. So we double the number of moles, and the volume doubled. Cool. Number 1 is true. Let's try number 2. This says the volume varies inversely with the pressure. That means that if the pressure increases, the volume should go down. We've kind of already seen this. This says that if we double P while holding temperature and number of moles constant, that the gas compresses to 1/2 of its initial volume. Let's see if we can do that. So we want to hold temperature constant. We want to hold number of moles constant. As long as we don't pump this button, the number of moles will stay the same. And we want to prove that if the gas compresses to 1/2 of its initial volume, if we double the pressure, the gas will compress to 1/2 of its volume. We can do the reverse, which is we can cut the volume in half and the pressure should double, right? I'm a little worried here that the pressure is that the reading will be too high. So I'm gonna get this to a normal value. Let's get these guys. Okay, so like 50. That seems fine. As long as I was worried that the pressure gauge was gonna go too high. Okay, we're gonna be holding temperature constant. And now what we're gonna do is we're gonna cut the width in half. So we're gonna go from 10 down to 5. Okay. So if what we saw was true, if I reduce this from 10 down to 5, so I cut the volume in half, and I tell you that volume is inversely proportional to pressure, what should the new pressure be? If we go from 10 down to 5, cut the volume in half. I know it's fluctuating. Say it's 53. Okay, you all think it's going to double, right? Yeah, so if we cut the volume in half, the pressure should double. That's what inversely proportional means. So we expect this to be something like 106. Let's see if that occurs. So we go all the way down to 5. Right there. And yep, there it is, 106. If we double it again. Oh, here's a question. Let's do this. What would the value of the pressure be if I go from 5 up to 15? So if I triple the volume, what should happen to the pressure? If I triple the volume, what happens to the pressure? Okay, Kate is correct. If we triple the volume, and those of you that are saying 1/3 is correct as well, it should go down to 1/3. So you think that's 35? So it's 106 divided by 3. I don't know what that is. What's 106 divided by 3? I can't. 35.3. That's exactly what you said. Perfect. Okay. So let's see if that's true. So we're going to go all the way up to 15, if it'll go that far. It will. It will go no farther. That's the biggest that we can go. So it's a good thing we chose that. And there you go. The pressure dropped by a factor. That's a third, right? Okay. What's the last one? The pressure is proportional to the absolute temperature T. If we notice absolute temperature, we have to use kelvins. If we double T, keeping the volume and the number of moles constant, the pressure doubles. Okay, so we have to keep volume and number of moles constant. We only want temperature and pressure to change. Only temperature and pressure can change. So all we really need to do is just hold the volume constant, I think. That's all we gotta do. And now, what we're saying is if we double the temperature, then the pressure should double. So, if I increase the temperature to 600 Kelvin, that's double the temperature, right? This is the whole reason why we use absolute temperature scale, right? is going from 300 to 600, you actually are doubling the temperature when you do that, right? Because 300 is half of 600, right? What about when you go from 20 degrees Celsius to 40 degrees Celsius? Is 40 degrees Celsius twice as hot as 20 degrees Celsius? It's not, right? Because you can have negative temperatures in Celsius, and 20 degrees Celsius is actually not that much below 40 degrees Celsius. In fact, you can survive pretty easily in 20 degree weather as well as in 40 degree weather. 40 degrees is really hot. 20 degrees is kind of cool. It's not so bad. But it's not that big of a temperature change, really, on the grand scheme of things. Okay, so again, we want to increase the temperature to 600. What's going to happen to the pressure? It's reading 35.6 atmospheres right now, or 35 atmospheres right now. When I double the temperature, what's it going to read? Something like 70. Yep. Okay, let's try it. So there we are. Go all the way up. Okay, a little too hot. We'll go down a little bit. There we go. Right about 70. 602 Kelvin. So, if you're a scientist and you've been working on gases and you realized all of these things were true, you can put them all together into one equation. Let's write down what they all say. The first one says that V is proportional to N, right? So V is proportional to number of moles. The second one says volume varies inversely with the absolute pressure P. So that means that the volume is proportional to 1 over the pressure. And finally, pressure is proportional to the absolute temperature. So pressure is proportional to temperature. And now what you have to do is you have to come up with an equation that ties all of these things together. Okay? And so the first thing you could do is you could say, okay, volume should be equal to number of moles divided by pressure, okay? And pressure is proportional to temperature, so I'm just going to put that over here because that makes it so the pressure is proportional to temperature now, right? And the only thing you need to do to finish the equation, right, is to just put some kind of a constant right here. Now, in this case, the constant that we use happens to be called R, the gas constant. But then you is this behind my picture? Probably is, actually. Kind of, not really. I'll move it over a little bit. You would get that equation right there, and then you would just rearrange it to be PV equal to nRT. That's all you do. I believe when you learn about this in chemistry, tell me if I'm right or wrong, you probably learn about things like Boyle's law and maybe Charles' law and a few other things for gases, right? The ideal gas law basically just pulls that all together. And, you know, the stuff you learn about in chemistry is the experiments that led people to understand this stuff, basically. Just want to mention a couple of other things about this. So a couple things we can do with this equation. One thing we can do is from above, we said that the number of moles multiplied by the molar mass of an object is equal to the total mass of the object. So if we replace little n in this equation with little m over m, so the mass of the substance divided by the molar mass, then we can get a new equation that looks like this. Pm over r times t is equal to mass over volume, but we know mass over volume is equal to density. So this is going to be an equation we're going to need later today in today's class. And you may need this on your homework as well. The density of a substance is equal to pressure times molar mass divided by the gas constant times temperature. Okay. One other thing that we can do. Oh, yeah. Sometimes the way this equation is used is if n is constant, then we can take all of these, well, some of these, and we can write the following equation. This is the primary way, I think, that you end up using the ideal gas law. Right here. It's right here. When the number of moles is constant, that means that PV over T is a constant, right? So if you know the pressure and volume and temperature at one point in time, and I tell you the pressure and volume at another point in time, you can tell me what the temperature is. That's what makes this an equation of state, basically, is because it relates these variables to each other, and if you know how they're related at one point in time, you can figure out what they're going to be later on. Okay? So let's do a really simple problem, which is this one here. In fact, I want you all to just do it yourselves and make sure you can actually see the problem here along with all the math that I have on the board. Try to solve this problem right here, number 18.1. Tell me what you get. There we go. You should be able to see it okay now. I'll give you a minute or two. You'll see what you need to do. Just plug everything in that equation. Use that version of R. What do you get for the volume? Oh, in RT, this should be P in the bottom. Whoops. That's right. Don't mind me is correct. The volume is equal to 22.4 liters. This is the volume. So check this out. This is kind of interesting. Any gas that we can call an ideal gas, it's going to have exactly that volume at standard temperature and pressure. Standard temperature and pressure is defined as what you see here. A temperature of 0 degrees Celsius, a pressure of 1 atmosphere. Any gas, hydrogen, oxygen, carbon dioxide, any gas, okay, that you choose will occupy exactly that much volume at standard temperature and pressure. Isn't that interesting? All types of different kinds of gases, they have different molecular masses, which means that some of them move faster than others, but that's the volume at standard temperature and pressure. Okay, let's do another problem. These are pretty easy. I think they're pretty easy, but maybe that's the problem. Okay, so here's one where the method that you want to use is the method where we're going to write like this. P1 V1 over T1 is equal to P2 V2 over T2. Let's read what the problem is. It says, in an automobile engine, a mixture of air and vaporized gasoline is compressed in the cylinders before being ignited. A typical engine has a compression ratio of 9:1. That is, the gas in the cylinders is compressed to 1/9 of its original volume. The intake and exhaust valves are closed during the compression, so the quantity of gas is constant. Quantity of gas is constant. That's how we know you use this, is because N is constant. What is the final temperature of the compressed gas if its initial temperature is 27 degrees Celsius and the initial and final pressures are 1 atmosphere and 21.7 atmospheres, respectively? So we're going to say we're going from state 1 to state 2, okay? This is, after all, an equation of state. So we're going to go from pressure 1, volume 1, temperature 1. We need to write down what all those are. and then we're going to go up to pressure 2, volume 2, temperature 2, and we just need to kind of fill each of these out. It says at the very end, the initial and final pressures are 1 atmosphere and 21.7 atmospheres. It says the initial temperature is 27 degrees. And we want to find final temperature, so this is what we're looking for here. Is what is the final temperature? It tells us that in a typical engine has a compression ratio of 9:1. That is, the gas in the cylinder is compressed to 1/9 of its original volume. There's two different ways that we can do this. If I call this V, okay, what would V2 need to be? So if it needs to be compressed to 1/9 of its original volume, should I write 9 times V, or should I write V over 9 here? V over 9, right? Okay. What I'm going to do, just to make things simple, is I'm going to call V1 9 liters, okay? And then I'm going to call V2 1 liter, okay? That just makes things easier. So it goes from 9 liters down to 1 liter. And then all we need to do, solve for T2. Okay, you can do some algebra and show that this is true. Multiply T1 to the right-hand side, multiply T2 to the left-hand side, and then divide by P1, V1. Then all we have to do is just plug numbers in. However, there's something we got to do here. We have to add 273 to this one. So we're going to get 300 Kelvin. This T1. Put that right here. This will not work if you don't do it in kelvins. In fact, I think we're at the point in the class where you can be pretty damn sure that every single problem you do, you're going to be doing in Kelvin. All right, so 300 Kelvin multiplied by P2 times V2. So P2 is 21.7. We don't have to convert it. We can leave it in atmospheres. That's totally fine. V2 is in liters. And then P1 was 1 atmosphere. And this was 9 liters, right? Let's see, 300 times 21.7 divided by 9. I got 723. Super, super easy. Anyone have any questions? It's pretty hot. That would be about, well, it should be hot because it's an engine, right? The whole point of the compression is to cause combustion, right? The compression itself actually causes an explosion, and then the explosion causes the piston to be pushed back up, and then the piston pushes back down again, and then an explosion happens, and the piston gets pushed up, and the piston pushes down again, an explosion happens, the piston pushes back up, and then you make sure that the piston is attached to a kind of thing where it creates a rotation, right? And that's attached to the drivetrain, which is attached to the axle, which makes the wheels go, right? That repetitive process. Compression, explosion, expansion, compression, explosion, expansion. That's what causes the piston to go in and out. We're going to learn a lot more about different types of engines in this class. We'll talk about how a diesel engine works. We'll talk about, in a lot more detail, the process by which an engine works. And that'll be, I think it's in the next chapter. Or the one after that. One of the two. I don't know. Pretty soon we'll be talking about, in more detail, what's going on inside of an engine like this. We'll talk about the Otto cycle, the OTTO cycle for diesel engines. Okay. Any questions? That's why cars have fans and water to regulate temperature. You're exactly right. That's exactly right. Yep. Or like antifreeze, right? Or whatever you got to keep that engine cool. All right. So we're going to do one more problem, but I think we'll take a break first because it's 7:30. Oh, no. We'll do this. Let's do this one real quick, and then we'll do this after the break. Okay, another problem. This says an empty aluminum scuba tank contains 11 liters of air at 21 degrees Celsius and 1 atmosphere of pressure. When the tank is filled rapidly from a compressor, the air temperature is 42 degrees Celsius and the gauge pressure is 2.1 times 10 to the 7 pascals. What mass of air was added? It tells us that air is about 78% nitrogen, 21% oxygen, 1% miscellaneous, and its average molar mass is 28.8 grams per mole. So looking at this again, it tells us we have a scuba tank. It's empty. It's not really empty, but we've got our scuba tank right here. And it has a volume that's equal to 11 liters. It has air that has a temperature, we'll call it T1, that's equal to 21 degrees Celsius, which is going to be, if you add 273 to this, you're going to get, what, 294 Kelvin? Tell me if that's right or wrong. And it says it's at 1 atmosphere of pressure, so the pressure is 1 atm. When the tank is filled rapidly from a compressor, the air temperature is 42 degrees Celsius. So we're going to get a new temperature of 42 degrees Celsius, which corresponds to 273 plus that is going to be 315 Kelvin. And it has a gauge pressure of 2.1 times 10 to the 7 pascal. So pressure 2 is going to be equal to, basically you take that number and you subtract, what do I have to subtract to get from gauge pressure to normal pressure? How do you go from gauge pressure? You subtract 1 atmosphere, but this is in pascals, so we're going to subtract 1.013 times 10 to the 5 pascals, which is also known as 1 atmosphere of pressure. Okay. Now this tank, the volume isn't actually going to change in this case, right? The volume is constant. I mean, this whole thing has a volume of 11 liters. The whole thing, you know, it's not. There's not. And we're pumping gas into it, so now the gas is basically just more and more pressurized. And the question is, what mass of air was added? Right? What should we do to figure that out? How can I calculate the mass of air that's been added? Yeah, so find it in moles. Okay. So we can figure out the number of moles that we started with here, right? We can figure out the number of moles we have right here by using this equation, because we have pressure, volume, temperature, and R as a constant. So let's do that. So N1 should be equal to, according to our equation, P1V over R times T1. And N2 should be equal to P2 times the volume, which doesn't change, over R times T2, right? Let's plug in the numbers. Pressure 1 is 1 atmosphere. The volume is in liters, so it's 11 liters. We divide by the version of R we're going to want now is 0.08206 liter atmosphere over mole Kelvin. And then we multiply by the temperature, which is 294. Okay, I want you all to calculate that for me there. Tell me what N1 is. Wait, we add it then, don't we? Hold up, you've confused me. Gauge pressure is equal to the actual pressure minus... Oh, yeah, you have to add it, don't you? We have to add 1 atmosphere of pressure. Is that what you mean, Kate? That's right. That's right. The actual pressure is going to be the gauge pressure plus atmospheric pressure. Is that what you're saying? We don't want gauge pressure, Kate. You understand that? We want the real pressure. We want the absolute pressure. Okay, cool. Sorry, I didn't think about this. I just put a minus sign. I forgot. We have to add it. Okay. Tell me what M1 is. You all can calculate that, and then we'll do N2. You got 0.456. Okay, great. This is 0.456 moles. Tell me if you all agree. I think that sounds right to me. And then for N2, we're going to have... let's use a different color. I see it's... There it goes. All right, so N2 equals P2. Now, this is in pascals. So this is going to end up being 2.11 times 10 to the 7 pascals, if you add those together. We need the volume, not in liters, but we need it in meters cubed. Pretty easy, you just divide by 1,000. So the volume is going to be 0.011 meters cubed. We divide that by R. We need the other value of R now, which is the 8.31. This was in joules per mole Kelvin. So we had to do this because it's pascals and meters cubed, so you want joules here. And then T2 is this one, 315 Kelvin. Okay, what's that one equal to? $88.7. Is that right? Seems like a lot. Okay. And now what we need to do is we have to do N2 minus N1, because that's going to be the air that we added. And then we have to multiply that by the molar mass of the air. And that should give us the mass of added air, basically. So we take 88.7 minus 0.456 multiplied by the number of grams per mole, which is given right there, 28.8. And we get an answer that is going to be the mass. So we take 88.7 minus 0.456 multiplied by 28.8. 2541 grams. That's what I got. Do you all agree? Not very much. 2.5 kilograms of air. Okay, great. Well, we'll take a break, and then we're going to solve this problem down here at the bottom. The time is 7:38, so we will take a break until 7:48.
Quick question.
Hold on 1 second. Yeah, that's right. Okay.
How come you would subtract the N2, molar mass N2 minus N1 when we're trying to grab the total? When do we
No, it says what mass of air was added.
Ah, okay. Okay.